Hello, Prosperivarians. The best school has come to stay in the city of Calabar. It is called Beryl International School. Take advantage of this opportunity now.
Tell me the best school, Beryl is the best. Tell me the best school.
Students, welcome to the second week of Beryl e-learning. I hope you are all doing well at home. And it's time for mathematics, Jss3 class. We're going to look at the topic sines and cosines of acute angles. Sines and cosines of acute angles. In our previous class, we talked about the tangent of an acute angle, where we used a right angle triangle to make illustration using our SOHCAHTOA. Now, it is also somewhat the same thing with the sines and cosines of an acute angle. We still use the right angle triangle to make our illustrations. So I gave us the SOHCAHTOA principle in the previous class, where we say the sines of angles is given as opposite all over hypotenuse, cosine is given as adjacent all over hypotenuse, and tangent is opposite all over adjacent. Now this principle is only true for a right angle triangle. And remember, we drew a right angle triangle in our previous class. Of course, this triangle ABC with our angle B being our 90 degrees. If we call this theta. Now, I said that the longest side is always called the hypotenuse. The longest side is called the hypotenuse, and it's always opposite our 90 degrees. The hypotenuse is always opposite our angle 90 degrees. And we also said that our opposite and adjacent side depends on where we have our angle theta. Our opposite and adjacent side depends on where our angle theta is situated. So at this point we have our theta here. That means the opposite will be this way, because this is the side opposite the angle. And we have our adjacent at this point because it is at the same base with our angle theta. If we have our theta to be here becomes the opposite and here the adjacent, as we said in the previous class, and of course our hypotenuse does not change. ABC with angle theta. Our sin theta is given as opposite over hypotenuse. So we have opposite all over hypotenuse, where our opposite is our line AB, because it's the side opposite our angle theta. So our opposite is line AB. We have line AB all over our hypotenuse is line AC. We have hypotenuse as line AC. Line AC. We represent line AB this way and line AC this way. So our sin theta, which is opposite over hypotenuse, we have theta here, opposite AB all over hypotenuse AC. So if you want to get cosine theta, we have cos theta, and from our SOHCAHTOA, cos theta is adjacent all over hypotenuse. So from our theta, the base side of our theta is the adjacent. So we have adjacent over hypotenuse, and our adjacent is line BC. So we have line BC all over our hypotenuse line AC. Line AC. So sine theta is AB all over AC. Our cos theta is BC all over AC. Giving a right angle triangle. Example, in the right angle triangle, ABC, in the figure below, find an expression. Find an expression for each of the following. Find an expression for each of the following. We have sin theta, we have cosine beta, we have sine beta, and we have cos theta. We draw the right angle triangle. Triangle A is called this our right angle triangle, angle B. We call this angle beta, and call this angle theta. Now, from our question to find sine theta, we see where we have our theta. The side opposite theta, tan theta is opposite all over hypotenuse from our SOHCAHTOA. From our SOHCAHTOA, sine is opposite all over hypotenuse, so we have opposite over hypotenuse, and the side opposite angle theta is line AB. This is the side opposite our angle theta. So we have line AB all over our hypotenuse, line AC. Our sin theta will give us line AB all over line AC. The next one is our cos beta. This is our theta and this is our beta. So we say cos beta will give us adjacent all over hypotenuse. Now, since this is the opposite of angle theta, this is the opposite of angle beta. But for sin beta, we now have opposite all over hypotenuse. Opposite all over hypotenuse. Our opposite is line BC. Line BC all over hypotenuse, line AC. Cos beta is, cos is adjacent all over hypotenuse. Cosine is adjacent all over hypotenuse. So adjacent all over hypotenuse, we have our beta, our adjacent is line AB. Line AB all over line AC. We have our beta, this is opposite, this is our adjacent line AB all over line AC. Then the next we have is sin beta. Sin beta we know is opposite all over hypotenuse. Opposite, sine is opposite all over hypotenuse. We go to our beta, the side opposite is line BC. You see? Line BC all over hypotenuse is line AC. Line AC. Then the next we have cos theta. We have cos theta. This adjacent all over hypotenuse. And we have our theta. The side adjacent to theta is this. We have line BC all over our hypotenuse. We have line BC all over line AC. Let me rush through it again. We have that from SOHCAHTOA that sine of angles is opposite all over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite all over adjacent. And we are given a right angle triangle where we have our angle beta to be 90 degrees, and we have our beta and theta. And for us to find sin theta, we apply the rule opposite all over hypotenuse. And our theta, the side opposite theta is line AB. Line AB all over our hypotenuse, line AC. So sin theta will give us line AB all over line AC. Our cos beta is adjacent. We have beta here. This is the opposite for beta, and this is the adjacent. The adjacent is line AB, and all over hypotenuse is line AC. Then we have our sine. For C, we have sin beta, which is opposite all over hypotenuse. That's line BC opposite all over AC hypotenuse. Then for our cos theta, adjacent over hypotenuse, we have our theta, and our adjacent, the base side of the theta, which is line BC all over hypotenuse of line AC. That is how to apply SOHCAHTOA in finding sines and cosines of angles. Now we should take note that I said in a previous class that the sum of these two angles must be equal to 90 degrees. So we are talking about tangent supermacric angles. The sum of these two angles must be equal to 90 degrees. It still holds for this sines and cosines of angles. In this case, the angles are not known. But if you are to find these two angles, you should take note that they are complementary angles, and so the sum of these two should give us 90 degrees. Also, let's take note that sin theta AB over AC is the same as cos beta. Sin theta is the same as cos beta. That's line AB over AC and line AB over AC. So, in a right angle triangle, the sine of this angle must be equal to the cosine of this. We will start solving problems where we have a known value to understand this better. In a right angle triangle, the sine of this angle must be equal to the cosine of the other complementary angle. So sin beta 2 is the same as cos theta. That's what we have here, BC over AC, BC over AC. So we now solve the problem where we have given sides. In the right angle triangle below, find expressions for each of the following. We have sin alpha, we have cos beta, we have sin beta, we have sin alpha, we have sin beta, and we have cos square beta. In the right angle triangle, we will have to find the expression for each of the following. We will first draw our right angle triangle. Okay, it's being drawn for us already. This one. Since we have a right angle triangle here, so this should be our hypotenuse. 13 is our alpha, and this is our beta. So we have to find sin alpha. We still apply our rule. We write it out. Sin alpha will give us what we know it should be opposite all over hypotenuse. And when we have our alpha this way, and the side opposite of alpha is this way. So we have 5 to be opposite, and our hypotenuse is 13. So our sin alpha will give us opposite over hypotenuse 5 over 13. Then next one we have cos beta. Adjacent all over hypotenuse. And we have our beta this way. This side is opposite our beta. And of course the adjacent is going to be the same base with our angle beta, which is 5. So our adjacent is 5. And our hypotenuse remains 13. So you can see what I say, that sin alpha is always the same thing as cos beta, because we have 5 over 13 and 5 over 13. So sine of angle is always the same as cosine of that angle. So the sine of angle is always the same as the cosine of the corresponding complementary angle. The next one we have cos beta. We have adjacent all over hypotenuse. So our adjacent will be 5, the hypotenuse will be 13. Sorry, cos beta. Adjacent to the hypotenuse. So we have, A is this, C is sin beta. Sin beta. This is B and this is C. Sine is opposite all over hypotenuse. And our sine, we have beta opposite is 12 and hypotenuse is 13. We have 12 all over 13. Here we have sine alpha plus sine beta. We have done sine alpha before, 5 over 13. We have 5 over 13 plus sine beta is 12 over 13. So we add these two fractions. Since we have the same denominators, we can just add the numerators. 5 plus 12 gives us 17 all over the common denominator 13. If you have the same denominator, you just add the numerators. 5 plus 12 is 17 all over 13. Pick out one of the denominators. Then the next one, we have to find cos square beta. Cos square beta. Now, cos square beta is like saying cos beta times cos beta. Like saying cos beta square. But since we are dealing with trigonometry, the square does not come this way. It's been expressed like cos square beta, meaning cos beta times cos beta. Even if you have theta here, cos square theta means cos theta times cos theta. So our cos beta is 5 over 13. We say 5 over 13 times 5 over 13. 5 times 5 gives us 25. 13 times 13 gives us 169. So our cos square beta is equal to 25 all over 169. That is that for cos square beta. Angles in finding right angle triangles. Using sines and cosine tables in finding right angle triangles. In our last class, we were taught how to use tangent table to find values of numbers using the tangent table. It's still the same process, just that for this one we use the sine and cosine tables. Now we're given a question to solve, but before I go to that question, there are some cases where we apply the Pythagoras rule. If we are given a right angle triangle to find an unknown side, given the length of the other two sides, we can apply Pythagoras rule. But there are cases where we can be given a side and an angle. In such cases, we can now use the trigonometric rule. So in this case, we have a right angle triangle. A right angle triangle ABC is such that angle B is 90 degrees, line AC is 15 cm, and angle C is 34 degrees. Calculate the value of line AB. Calculate the value of line AB. A right angle triangle ABC is such that angle B is 90 degrees, line AC is 15 cm, and angle C is 34 degrees. Let's calculate the length, the value of line AB. The first thing to do is to draw the sketch of the right angle triangle. You sketch it. You sketch this triangle A, B, C. It's such that angle B is 90 degrees, so our angle B is 90 degrees. Line AC is 15 cm. Line AC is 15 cm. Angle C is 34 degrees. Angle C is 34 degrees. But to calculate the value of line AB. The value of line AB. Now, for us to do this, we use our secateurs. We cannot apply Pythagoras rule here because we only have one side. As I was explaining earlier on, we can only apply Pythagoras rule, we have two sides and one unknown. So in this case now we use our trigonometry, that's a secateur. Sine of angles will give us opposite over hypotenuse. Since we are interested in AB, so we use the one that relates with this. Sine 34 will give us opposite. Let's look at one. Opposite all over hypotenuse. We cannot use cosine because we are interested in line AB. So we say, we first establish that sine theta is opposite all over, I call it sine C, since we are dealing with angle C. Opposite all over hypotenuse. Now, C is 34, so we have sine 34 degrees is opposite, which is line AB. We have our 34 degrees here, and the side opposite is line AB. So we have line AB all over our hypotenuse, which is 15 cm. Line AB all over 15 cm. So that will give us, we cross multiply, just like saying all over 1. We can cross multiply to get, once we cross multiply, we get we now have line AB equal to sine 34 degrees times 15 cm. That's line AB times 1 is equal to line AB, and sine 34 times 15, so you have to cross multiply. So now, we were taught how to use the tables in our previous classes. Whereas when we resume, I will take time to teach you how to use the table. For those of you still having challenge in using the 4-figure tables. But if you use it to check sine 34 degrees, we would have sine 34 degrees to be 0.5592. 0.5592 times 15 cm. From here we cross multiply. We have line A will be equal to sine 34 degrees times 15 cm, and our sine 34 degrees will give us 0.5592. We still multiply by 15 cm. If that is multiplied, we have our line AB to be 8.388 cm. 8.388 cm. You can approximate to 2 decimal places. That will give us 8.39. We round up since the next number is more than 5. So we have 8.39 cm as our line AB. So this point is 8.39 cm. We've solved another problem for a better understanding. In the right angle triangle, below, calculate the length represented by x. Calculate the length represented by x. We have a right angle triangle. We have 30 cm. We have an angle here 47 degrees. We have an x. How do we find our x? I told us earlier on that once you are given one side out of 3, you cannot apply Pythagoras rule for a right angle triangle. You can only apply Pythagoras rule when you have 2 sides and 1 unknown side. So in a case like that, we have just a side and an angle, we still go with our SOT as well. So for us to find our x, sine, if we say sine 47 is opposite all over hypotenuse, the x is not involved. But we say cos 47 is adjacent all over hypotenuse, then the x is not involved. Remember to look for x. So we now use cos instead of sine of angles. So cos 47 degrees will give us our adjacent. Remember, adjacent sides will be on the base because we have an angle. So our cos 47 degrees will give us adjacent all over hypotenuse. So we first established that cos theta from our SOCAT is adjacent all over hypotenuse. So we now say cos 47 degrees. Cos 47 degrees, you have our x all over 30. We have x all over 30. So at this point we cross multiply. So we now have x will now give us cos 47 times 30 degrees. Sorry, times 30 cm. So we now find what cos 47 is using our 4-figure table, and that should give us 0.682. 0.682. Then we multiply it by 30 cm. So if that is multiplied, we have 20.46 cm as our x, using 2 decimal places. 20.46 cm as our x. So I will just take it through. If in the right angle triangle below, calculate the length represented by x. And we have x on the base, the same base with the angle theta. Since we are represented in our line x, we cannot use sine of angle because from SOHCAHTOA, sine of angle is opposite all over hypotenuse. We are not interested in this side, but x. And cos x is given as adjacent all over hypotenuse. So we say cos 47 degrees is x adjacent all over hypotenuse of 30. We have to check cos 47 degrees is x all over 30. At this point, we cross multiply to get, when we cross multiply, we have this x times 1 will still give us x, and cos 47 times 30 as we have on the board. With our 4-figure table, if we check cos 47 degrees, we get this 0.6820. X gives us 0.682, then times 30 cm. Multiply this together, we get this by approximation to 2 decimal places. That's 20.46 cm. That means our value of x on the base is 20.46 cm. Next, we look at how to apply sines and cosines of acute angles. Application of sines and cosines of acute angles. Remember in our previous class we talked about an acute angle. We said their angles are less than 90 degrees. Now we have a question. A ladder inclined at an angle of 36 degrees. To the horizontal, leans against a vertical wall. Vertical pole, rather. If the ladder is 7 meters away, from the foot of the pool, calculate the length of the ladder. Calculate the length of the ladder. The ladder inclined at an angle of 36 degrees to the horizontal, leans against a vertical pole. If the ladder is 7 meters away from the foot of the pole, calculate the length of the ladder. Now in this case, the diagram is not given. You have to read the question and draw the diagram. So the diagram is part of our solution in this case. So a ladder inclined at an angle, we can draw the ladder. Since we are told that the ladder leans on the vertical pole, the ladder is inclined at an angle of 36 degrees to the horizontal. The horizontal is this way, this side is the horizontal, and our ladder is inclined at 36 degrees to the horizontal ground. So this is our 36 degrees. It leans against a vertical pole. It leans against a vertical pole. These are vertical pole. These are pole. And the ladder leans against this vertical pole, making an angle of 36 degrees to the horizontal ground. If the ladder is 7 meters away from the foot of the pool, we have our pool and the ladder. It is 7 meters away from the foot of the pool, so here is 7 meters. Calculate the length of the ladder. The length of the ladder is this way. Let's take it again. The ladder, you have a ladder inclined at an angle of 36 degrees to the horizontal. You have the ladder inclined at an angle of 36 degrees. It makes 36 degrees with the horizontal ground, not with the vertical pole, with the horizontal ground. See this way. It leans against a vertical pole. See our pole, our vertical pole. If the ladder is 7 meters away from the foot of the pole, the ladder is 7 meters away from the foot of our pole. So this side is 7 meters. But to calculate the length of the ladder, foot will represent as x. So to calculate the length of the ladder, will represent as x. Using our SOHCAHTOA, sine 36 this way will be opposite. So we cannot use sine of angle because sine 36 opposite all over hypotenuse. This side is opposite. And we are interested with our hypotenuse, which is x. Now we cannot use adjacent. Cosine. Cos theta, as we know, is adjacent all over hypotenuse. So we say cos 36 degrees will give us our adjacent. Remember, it's on the same page with our angle 36. So adjacent is 7, all over hypotenuse is x. Cos 36 degrees is adjacent to our hypotenuse. Now adjacent is on the same page with our 36 degrees, all over our hypotenuse. So we have cos 36 will be equal to 7 all over x. 7 over x. At this point we cross multiply.